Good evening. It is wonderful to see everyone this evening. Last couple weeks we have begun our study on essentially what we're titling just apologetics in general, meaning a defense of what we believe, in particular we've been focusing on a defense of what we believe in terms of God being the creator of our universe. And we're going at that, in this case, from a very specific route so far. We are looking at different aspects of creation to see, kind of really dig deeply into things that point back to God. We can see, as we even look at in Psalm 19, for example, the idea that the created world is meant to point us back to God, that God's fingerprints can be seen all around us. And so we're looking at it from that standpoint, focusing on the created things that we see around us as a means of how could this be anything but a reference back to God and His power, because what else could accomplish such amazing things? Last time, not last Sunday, but last time that we had this class on Sunday evening, we looked at DNA and just how amazing the DNA is and how far beyond even our own technology when it comes to like computers and things like that, these tiny little strands that we can't even see with the naked eye hold more information per size than anything we have come up with in terms of our own technology. We're going to continue in a similar vein tonight as we look at cells. Now, of course, DNA is within a cell, and if DNA is this amazing, well, we're going to look at the whole cell in itself tonight and just look at some things about cells that kind of help us to see what God has put into place. Now, as we start off, you notice that the title of the lesson is Cities on a Pin. I want you to think about, if this thing will move. I'm not sure why. But I want us to think about a pin. How many of y'all have seen any kind of sewing needle? I'm not saying you have to have used it, but oh, there it goes. If you've seen a sewing needle, right, we're not even talking about like a knitting needle or anything like that. We're talking about a sewing needle. If you've ever seen a sewing needle, those things are already small. But we're talking about the tip of the average sewing pin or sewing needle. The tip of one of those things, if you actually just sit there and look at it, how many of y'all have ever tried to see if you could actually see the pinpoint of that pin? It's almost impossible to even see the point of a pin with the naked eye, right? In fact, the width they estimate for the average pin, it's about 0.02 inches wide, or half a millimeter. A millimeter, very tiny, tiny unit of measurement. Tiny, tiny little thing on the edge of a pin, right? The average cell in your body is so small, you could line 20 cells up and it would go from end to end of the tip of a sewing pin. That's how small we are talking about when we're dealing with cells. Tiny, tiny, minuscule little things. You could fit 20 of them in a line on the head of a pin. Now, we know they're small, right? Most of us are familiar with the idea that cells exist, that our bodies are made up of cells, all that kind of stuff, especially things in our medical field in terms of treatments for diseases like cancer and stuff like that, really focus in on the cellular level at times. So we're familiar with this idea of cells, and we're familiar with the idea that they're small. But I want us to actually think for a little bit tonight about some things that we see in the cell itself. Now, you might be thinking, okay, are we about to go back to biology class? Well, a little bit, but not really. Because what I want us to do is I want us to compare the functions of a cell to things in the, the macroscopic world, like the world we can see. I want us to compare it to things that we can see and recognize how these all work together. Whenever they first thought about maybe cells and atoms and things like that we can't see with the naked eye, maybe those exist, it's interesting, even back in ancient Greece, there were some philosophers and scientists, if we want to call them that, that began to theorize maybe everything around us is made up of smaller things. Kind of like how if you look from a distance, when you go to the beach, or even when you go around here somewhere, right, if you see a sandy area, can you make out the fact that there are little pieces of sand everywhere that make up that area if you're standing at a distance? You can't really see it. If I'm, on the other side of the street and I look over, I can just see sand, right? I can't see sand like little pieces of sand. I just see a ground full of sand. It's only when I get closer that I can see there's actually a bunch of small little particles. They theorize, okay, maybe it's, something like that the whole everything around us, people and things and whatever, are just made up of these small little things, whether we're talking about atoms or cells or whatever. But they theorize those must be the smallest pieces of anything that exist. Because surely, if it's that small, it has to be simple. Surely, if it's that small, it has to be very just straightforward and not much to it. Have you ever looked closely at a grain of sand? Now, I know there's some things that are complex about a grain of sand, but have you ever just held sand in your hand? What is it? It's just a chunk, right? It's not like you hold a magnifying glass to sand and it's, a snowflake or something like that. Sand is just this chunk of something, right? It's just kind of not really in a particular shape or design. It's just kind of there. That's what they thought that cells and things like that must be. Oh, how wrong they were. Every cell in your body, in fact, is like a city. And we're going to talk about that as we go through here. And I want us to kind of work together to see how this might look if we blew it up to a big scale. Because really, every single cell, remember, one of these things that you could line up 20 of them on the head of a pin, is like its own city. It has structures, kind of like we have buildings that are specialized for every single function. So I want us to think about just some of these functions tonight, some of these structures within the cells. Again, I'm trying not to focus so much on all the complex biology of it. I don't know most of the complex biology of it anyway. But I'm trying not to focus so much on that and focus more on what it does in the actual cell. So I want us to think even about Wellington, Texas, out here. What are some of the buildings that we have in Wellington, Texas? Anybody? Okay, we have the courthouse. Good. What else? School. Okay. What else? Grocery store. Okay. Do what? Bank. Okay. All these different buildings, and all with people working in them, right, serve different functions. For example, when we go to the grocery store, it's because we need to get food. Well, if you think about where we get the food from, well, that has to come from somewhere else. Around here, right, even though we don't necessarily farm as much food, as far as the cotton anyway, still we think about farming, that's where that comes from. It has to be processed before you can get from the grocery store. But then you go get from the grocery store and it helps us stay alive, all those kind of things. We have the courthouse, that's where people work that help the city run and all that kind of stuff. We see how every part of the city works together to help the city work. Let's start by thinking about the cell. Again, we're not going to analyze every piece of this. This is a basic, and when I say basic, I mean very basic, diagram of an average cell in your body. Now, don't worry about all of the labelings and stuff like that. But if you just notice all these different shapes, it's not like it's just a blob. Used to, when people first discovered cells, they thought it was just this tiny little sack full of fluid, and that was it. It was just this very simple structure of just, it's basically like if you took, instead of sandbags, if you took like bags of like Ziploc baggies with water in them and filled it up with water and just stacked a bunch of them on top of each other into a shape. That's what they thought cells were. But in fact, it's got all these different structures inside of it that fulfill different functions. Just like in a city on a large scale, we have all these different buildings that have all these different functions and they serve different purposes, people working in them accomplishing different things that all help the city run. So let's start with that big thing in the middle. The nucleus. Nucleus, in many ways, functions like City Hall, or the courthouse in our case. When you go to the courthouse, who works in the courthouse? Okay. What are some of the people what are some of the jobs of the people that work in the courthouse? Okay, tax collectors. First one that comes to raise mine. What else? Who else works in the courthouse? Okay, the JP, judge, yep. A lot of people that work at the courthouse. Now, arguably about the tax guy, I guess, but in general, whether you have the tax guy, the justice of the peace, I think was it the assessor or something like that, all these different people that work there, what is their overall job as it relates to the city, and in our case, the county? Well, they make sure everything's organized, right? They make sure everything is working like it's supposed to, everything is structured like it's supposed to. That's essentially what the nucleus of the cell does. Now, we'll talk more about the chromosomes inside the nucleus in a second, but the nucleus is basically the hub. If you didn't have a nucleus in a cell, kind of like if we didn't have any kind of city government, no court system in the county, no city manager, nothing like that. If we didn't have any of that, then as far as the actual city goes, maybe we just go about our merry way, but as far as the actual city goes, there would be nobody making sure everything is organized and done the way it needs to get done. Well, that's what the nucleus does. It makes sure that everything is working like it's supposed to based on the records that are kept inside of it, which gets us to the chromosomes. Chromosomes, kind of like the clerks. If you go into, I'm assuming it's the courthouse, although I haven't looked in all there. Actually, no, I have. I have looked in a couple of the rooms where they keep some of the records. Have you seen those walls of files in the courthouse? If you had to sit down and read all those files, how long do you think it would take you? It's a ridiculous amount of information, right? And we have about 2,000 people in this whole county. So it's very minimal in terms of the information we have to have here as opposed to larger city halls or larger offices for the city clerks and so forth. And yet that's how much information. Now, what kind of information is stored in those records? Okay, deeds, good. So this goes here and this goes there. This belongs to this person, this belongs to that person. What else? What other kind of records do they have?
Marriage.
Okay, good. Marriages and deaths, so kind of keeping everything straight as far as, this person goes with this person and this goes here and this goes here. This is kind of how this is supposed to connect or this person is supposed to connect, all those kind of things. Well, we talked about DNA a little bit, and we talked more about it in terms of its ability to store information. But the information that is actually stored in it, amazingly, we think about keeping records of things like deeds, and I think business licenses would be another thing, and births and deaths and marriages and all these kind of things. Well, very similar types of records are stored in the chromosomes, in the DNA. You have records, for example, of how to connect different parts of the cell. This thing in the cell is supposed to work with this thing. This thing kind of is married to this thing, if you will. They're supposed to be a couple. They're supposed to work together over here. This thing is designed to function alongside. It all works together based on that information. The chromosomes, of course, are held in the nucleus, just like city clerk usually works in a city hall or a courthouse or something like that. And all of this, again, is designed to make sure that the city can run the way it needs to. Have you ever, most of us probably have experienced something along these lines, have you ever needed your birth certificate or your marriage license or a certificate of death if someone's passed away? Have you ever needed those to accomplish some very, very important things? Imagine if there was nowhere you could go to get those records. Imagine how quickly, just on an individual level, life would get way harder for you all of a sudden. Well, the same thing is true with the cell. If there's no records, if there's nothing that can organize, can get everything working the way it needs to be within the cell very quickly is going to just fall apart. So the chromosomes fulfill that role. Well, let's talk about another aspect of the cell. Mitochondria. It's a fun word to say. Mitochondria are like power plants. Now, we kind of take electricity for granted in this day and age, and it's understandable. We've been used to it for a long time. But a lot of times we don't think about the fact that electricity always has to be produced. And we're talking about every home pretty much that exists in the city, in the county, in the state, in the country, all those being powered by power plants, and then it has to be distributed throughout the entire city, country, all that kind of thing. And the amount of not only power that you have to produce, number one, but then the amount of infrastructure that you have to distribute that power everywhere. Anyone ever been to or worked in a power plant, taken a tour or anything like that? Anybody? Jerry, what does it look like in there? What does it look like inside a power plant?
They wouldn't let me in. We just went in the administration building and seen the movies.
Okay, good. How big was the power plant?
It's one of those silos.
Okay, good. whenever you go to a power plant, even if it's a smaller power plant, it's amazing just the scale a lot of times, depending on how much they're having to do and what all they're having to what am I saying? How they're having to divide it out and distribute the power. But depending on the type of power plant, usually you have something along the lines of like a network of coiled wires and magnets type things, if I remember right. Now, it depends on the power plant, and some of the technology may have changed since I last studied some of this. But basically, you have to have a lot of space to do all this, so that the motion usually caused by like burning coal or running water, if it's like a dam or a hydroelectric plant or something like that, that can be converted into energy. Now, when you think about that on this kind of scale, even for Wellington, right? Just a couple thousand people. Think about how much electricity has to be generated for just a small town like ours to function. I mean, I don't know about you, but I don't think I could manage to produce that much energy if I was just left to my own devices, even if I had all the materials. It's a crazy amount of electricity. I mean, just this one building, think about all the electricity you need to run the lights and to run the power and all this kind of stuff. The mitochondria in a cell is the power plant. There are multiple mitochondria in a cell, as a matter of fact. And each one of these mini power plants, basically what it does, we're going to oversimplify it, basically it takes raw materials and it takes oxygen and it runs through a process. Sometimes we call it like burning, like combustion or something like that. It's not literally everything's on fire in your body. That's not quite an accurate description. But basically, it merges the oxygen through a chemical reaction with these raw materials, and through that it produces energy. And that energy is then distributed throughout the whole cell so that every other building, if you will, in the cell, including the nucleus, can do what it needs to do. Now, I just want us to keep in mind, your cells don't stop working. At night, is there more electricity or less used than during the day in Wellington? Significantly less, right? Now, sometimes people stay up or are doing things, some people have to work nights, but generally speaking, you have way lower power necessary at night than during the day. But for your cells, although that also can be true, you are resting after all, but inside the cells themselves, they're constantly working 24/7. They're constantly functioning to do what needs to be done, some of which we'll talk about here in a minute. And they need power to do that, which means you have these power plants working constantly to provide power for the cells. Let's move on. Ribosomes. We don't have to memorize any of these, by the way. There's not a quiz or anything at the end of this, but I'm just giving you the names of these structures. Ribosomes are another one of these structures in cells. Now, if you look around Wellington, how many of these buildings that are necessary for the town to function, how many of those had to be built by somebody? Well, all of them, right? Well, that means you have to have somebody who can actually build buildings. Never mind the fact that you have to have the people working in the buildings to actually help it function, whether it's people working in a bank with financial expertise, or people working in the grocery store who know all the wholesalers. We're not even going there yet. We just have to have the physical structure there that can work for the purpose that it's working for. Well, also, you need someone who can construct those buildings. Well, that's what ribosomes do. Basically, ribosomes, they make all of the other, they make all of the components to make all the other structures. So really just kind of not wanting to get in the weeds on it, but basically there are building blocks for all these other structures that you make within the cell. All of those are made in the ribosomes. Without ribosomes, nothing in the cell would exist because you wouldn't have anything to make it with. But with the ribosomes, they build it all. So they're the ones who come in, and we go from, a flat plain in the panhandle of Texas to a town with buildings and houses and all this kind of stuff. That's what the ribosomes do. And of course, they do this at the direction, in this case, of the nucleus. Kind of like if the city says, hey, we need to build something for the town to function. Let's say we need, a waste management building or something like that, or we need what would you call that? Not an outpost, but a building for like some of the power workers to have a place to leave their trucks and go and come and all that kind of stuff, then we need to bring in somebody to do that. Well, there you go. That's the ribosome's function as we're looking at the cell. We also have what are called vacuoles. Vacuoles are basically little warehouses. They store materials for later use. For example, if you have, let's just use a coal plant, for example. If you have a power plant that runs on coal, well, it takes a lot of coal for that power plant to run. And so you always need to be shipping coal to the power plant, but you can't burn it all at once. In fact, that would completely defeat the purpose, wouldn't it? So what do you have to do with all the coal until it's ready to be used? Well, you have to store it somewhere. Well, that's what vacuoles do. They know what needs to be stored. Remember, some things need to be gotten rid of instead, right? Imagine if, let's say there's a small like storage area in town, a warehouse, whatever we want to call it. And let's say that the person who is running the warehouse didn't know the difference between, I don't know, let's say tires, Danny. They're storing up tires for you to use at your shop. They didn't know the difference between tires and garbage. And so they stored both in the warehouse. Well, that would cause a problem pretty quick, right? Because one of those things need to be kept around and the other one needs to be gotten rid of. Well, vacuoles know they not only can store things, but they know which things to store and which things to get rid of, which is crazy. Then you have another really fun one to say. Man, say this one 3 times fast, all right? Endoplasmic reticulum. Endoplasmic reticulum. Endoplasmic reticulum. All right. The endoplasmic reticulum. That is another structure within a cell. If you've ever been to a place like Dallas or New York or some of these bigger cities, they have public transit. They have these like trains that run, and they're not trains in the sense that we see out here of like just going down the tracks delivering stuff. This is for people to go back and forth. In New York, it's usually like a subway system. In Dallas, it's more of like an above-ground system, but same difference. You have these set areas where you can go from point A to point B, and that allows people ultimately to get everywhere they need to get throughout the city. Well, there is a system like that in the cell. In every single cell, there is a system that allows, we're not even talking about function in terms of producing power or producing, nutrients or anything like that. We're talking about just getting from point A to point B within the cell. Well, there's a system in place to do that as well. Just like maybe, let's take it down to Wellington. In Wellington, we don't have a public transit system, but what do we have instead to help us get from point A to point B? We have roads, right? We have streets that go back and forth in the city. If I want to go from Bowie Street over to Haskell, well then, there's a way to get there, right? We've mapped all that out. Well, the same thing is true in the cell. Not only that, we have what are called transport vesicles. So we already talked about vacuoles. They're kind of the static storage area. They store things. How many of y'all get stuff delivered by Amazon? Anybody? It works awfully well, especially out here. I mean, we don't have a whole lot of brick and mortar stores that we can go to. They're close. But man, Amazon comes in clutch, doesn't it? They're able to bring us just about anything we need, even if it's kind of far away from most of these other places where we're ordering it from. Well, the same thing is true within the cell. Even though it's so small to us, within a cell, if you're one of these tiny little proteins or something like that running around a cell, we're talking about a big area, right, from that perspective. So you got to have transport from one area to the other. Well, these vesicles, basically, they create a barrier around something that needs to be transported, and then it uses some of that power that's generated by the mitochondria, and it'll propel itself through the cell from one end to the other. Sometimes it'll deliver something that needs to be taken from one place to the other. Other times, these transport vesicles are also waste management. So instead of a delivery van, they're a trash truck, and they grab the stuff and just chuck it out of the cell altogether. But either way, they move the things around that need to be moved around. We have that here in town, right? People pick up our trash. People, again, deliver stuff from Amazon. People deliver the mail. All those different kinds of things need to be moved from one point to the other. Not to mention, we all have cars. We need to move ourselves from one point to the other. All of that is taken care of with these transport systems inside these tiny little cells. Now, I just want to pause here. We're just about done going through all this. I just want to pause here and say, I'm not exaggerating the function of these cells. If anything, we're oversimplifying the complexity of how all these things work and the purpose that they serve in the cell. When we think about a city and comparing these things to a city, what we do in a city is generally crude compared to what is done in a cell. Meaning it's done with so much more efficiency on so much of a more advanced level than we do in an average city. But let's look at one more thing. The cell membrane. Cell membranes are fascinating. So we talked about a cell kind of being like a sac almost. You have this membrane around the cell, but it doesn't just hold everything in place. It has a very, very important function. Now, you might have seen in, not even ancient times, but several hundred years ago, most towns would have walls around them. Why would they have walls around the town? Protection, right? If you're in the Americas, then you could be attacked by Native Americans or by various other tribes people or different things like that. If you are in Europe during a certain time, constantly there were like barons and knights going at each other and all this kind of stuff. Today, we don't really have, what shall we say? We don't really have physical walls. What do we have instead to protect the city? Do what? Okay, one thing we have is police. They are allowing us to protect the city. Why don't we have walls typically around cities anymore? Okay, good. Too expensive for one thing. Why else?
Upkeep.
Okay, good. Upkeep. Why else? Okay, good. There's a different dynamic now in terms of what happens. Meaning the threats that we face usually aren't someone's going to surround the city and try and starve us out and take us over or something like that. That's not really the era we live in now. And yet, think about our borders. Whether we're talking about our country's borders, sometimes depending on, we're talking about like states' borders, something like that, especially country borders, or even think about like gated communities and things like that. Oftentimes, they have some kind of literal barriers. I'm not going to get all political about it, but right now, there's a wall going up on the southern border, right? Now, whether you like that or you hate that, that is designed to keep barriers to where the people that are supposed to get in, and the people that aren't supposed to get in, don't get in. Even in a gated community, if you've ever seen these gated communities where people live and they have houses, well, why are they gated? Well, because even though maybe the city doesn't have a wall around it, there's meant to be some security so that primarily the only people that go in and out of the gated community are the people that live there and people that they invite to their houses. And so there's a little more degree of privacy. Well, that's how a cell membrane functions. It functions like the borders of a country or the checkpoints of a gated community. They're not called checkpoints, whatever they're called, the gates of a gated community. Basically, the cell membrane is so intricately designed. You have these two layers of lipids, and no need to go into what that is, but basically you have these two layers, and then you have all these other things that are kind of put in between there, and they can literally tell what should and shouldn't go in or out of the cell. They're able to detect, just like if you have someone in a gated community, and they say, oh, hey, you live here, come on in. Oh, hey, could you tell me what you're doing here, right? Well, you have these small little proteins and things that are able to tell, hey, you belong in here, you're a nutrient that the cell needs, get on in here. And then another one, no, I'm leaving the gate closed, I don't want you in here, you're going to hurt the cell. It's able to do that very thing. And while we have to erect specific structures or have people like policemen or others keeping security uptight for our communities, this is just a very simple, really hardly couldn't even be simpler, structure around every single cell that is able to do that on a microscopic level. So, hopefully, we tried to kind of connect that to things you're familiar with. Like I say, I was trying not to go just focusing on the biology part of it. As we said, this is not an exaggeration of the function of these things. It is very legitimate to say that every single cell that we have in our bodies functions like one of our cities. It's very legitimate to use that. In fact, I'll just be upfront. The kind of skeleton that I used to put a lot of this together was a study guide for a high school biology test that someone came up with using these comparisons to try and teach students the basic functions of cells as they're in biology class. This is not something that, creationists have come up with, and it's really not nearly that complex or anything like that. No. In fact, there's a lot of people who will tell you that I really didn't do any of that justice just now. It's way more complicated than that. It's way more efficient than that. How could such an elaborate system come into being without intelligence? Even a town that's on the smaller end of things like Wellington. If someone walked into this town and looked around and saw the bank and the grocery store and the roads laid out and the courthouse and all these kind of things, would anyone in their right mind, we were joking earlier, me and Danny and Ray were, would anyone in their right mind say a tornado had come down through the panhandle and left the city standing here? Nobody would say that. Not even someone who thinks that happened on a different scale, right? Nobody would say that. Every single cell in your body is more complicated than Wellington, Texas, in terms of how it functions. It works better than Wellington, Texas, in terms of how it functions. That's not a comment on any city officials or anything, okay? That's just any human design for a city or functions like that. We're not very efficient in how we do it. There's a lot of time wasted. There's a lot of energy wasted. There's red tape. There's inefficiency. There's all these kind of things. That just doesn't happen in the cells. Generally speaking, cells are fine-tuned to a ridiculous degree. Every single one of them, like a small little city in your body. But here's the crazy thing. That's one cell. Anybody want a wild guess how many cells are in your body? Anybody? Oh, come on. Somebody have a wild guess. Come on. How many cells do you think are in our bodies? We're familiar with big numbers at this point, right? Our national debt is like what? No, I'm just kidding. Any guesses?
Got lots of zeros.
Yeah, okay. 30 trillion cells in one human body. Not million, not billion, trillion cells. 30 trillion cells in every single human body that is sitting in these pews tonight. 30 trillion tiny little cities fine-tuned to do exactly what they need to do to all work together, 30 trillion of them, to make your body function. One of the cells that we just talked about, it's unreasonable to think that that just happened. But every single one of us has 30 trillion of those little things just running away, functioning exactly how they need to function, doing all the things they need to do. It doesn't work any other way than to say this has to be designed. There's a book, I have not yet had the pleasure of reading it. I've wanted to for a long time, I just haven't gotten around it. It's called Darwin's Black Box. And it's about a lot of these very concepts that we've looked at tonight. The reason it's called Darwin's Black Box, people didn't know about cells and the makeup of cells when Darwin proposed his theory of evolution. And the argument of the book is there's no way that Darwin would have proposed this theory in the first place, and certainly no way anyone would have taken any kind of credibility or attached any kind of credibility to it if they had known how complex things are on a cellular level. Because that kind of complexity can't just happen. Not it's improbable that it can just happen. Not it would take a whole long time for it to happen. It can't happen. We've talked about before. Anything that has less of a probability than 10 to 150 zeros, right? 1 in 10 to the 150th power. Anything less than that, it can't happen. It's literally mathematically impossible. A single cell coming into existence is way, 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 way beyond that threshold. And we've got 30 trillion in every single one of our bodies. The conclusion that we ought to come to is quite simple. This points us to God. The psalmist said, I will praise you, for I am fearfully and wonderfully made. We haven't even talked about the things that we can see in our bodies. Structures like the eye and the various organs that we have. We haven't even talked about that. We're purely talking about the tiny level that we can't even see with the naked eye. And already, there's no conclusion we can take except God has done an amazing, amazing work in how he made creation. And I would argue he's done it to point us back to him. That's always the takeaway we should have from every single one of these discussions. This is meant to point us back to him. Even people who have heard evolution all their lives and have gone into the scientific field, many of them have begun coming to the conclusion, there's got to be something else to this. There are organizations now that are being formed. It sounds weird, but they're called ID organizations, and that may not be the official name, but Intelligent Design, ID. Basically trying to say, listen, we've got to open up scientific dialogue around the possibility of some kind of intelligent design, because this doesn't work. Just from a purely scientific perspective, this doesn't work unless there's intelligence involved in all of this. I will praise you, for I am fearfully and wonderfully made. What an amazing thing to consider as we think about what God has done in the creation of, in this case, the building blocks of our bodies. As always, the Lord's invitation is open. If there's anything we can do to encourage you, I hope that you will recognize that we all as a family of God, want to help each other. If there's something we can do, we ask you to let us know. And we ask that, as always, that we just help to encourage and strengthen one another and remember things like this to help us to recognize that we serve an amazing God. If there's anything we can do, please let us know as we stand and sing.
Softly
Tenderly Jesus is calling.